Hi class, welcome back. I'm Dr. April Strom, and in this video, we're gonna see yet another example of integration by partial fraction. But in this problem, we have a slightly more complicated denominator to attend to. Specifically, this power of 2 sort of messes everything up in terms of our flow. If that exponent of 2 was not here, this problem would work very similarly to the last example that we did with distinct linear factors. But here, because of that power of 2, I have to attend to how to expand this particular fraction into multiple fractions and then figure out what their denominators and appropriate numerators would be. Okay, so let's take a look here. So let's start with the integrand, the whole fraction to begin with. We have the 10x minus 2x squared and then divided by the x minus 1 squared times our x plus 3. And you notice I'm just dealing with the fraction itself, the integrand in my problem. And I'm going to need to decompose this one fraction into multiple fractions and then solve for the new numerators, put that back together again, and then go back to my original problem to actually deal with the integration. Okay, so in this problem, because I had that more complicated denominator, as we talked about, we need to decompose this actually into 3 separate fractions, and here's what the numerators and denominators will look like. So I will have one fraction plus a second fraction plus a third fraction that I'm going to have to deal with. The denominator of the first fraction is going to be x minus 1 by itself, let's say, x minus 1. The next denominator will be an x minus 1 squared, because we need to attend to that particular multiplicity of that linear factor being squared. And then ultimately, when we're finding this common denominator of all 3 of these fractions, it still needs to be equivalent to this one over here, this denominator here. The last fraction will have a denominator of an x plus 3. So those are all of my pieces, and I don't really need parentheses around this denominator, so I can erase those. Certainly I do need them here for the exponent. Now, because I don't know what the appropriate numerators are, I'm gonna yet again decide to call this numerator A, this one B, and my third one C, since I have no idea. But this makes things more complicated because now I have 3 unknowns that I have to algebraically solve for. So much in the same way of the last problem where we went through and took this rational equation and multiplied across to clear the fraction, I'm going to do that same process here. And when I do, I'm going to take my denominator that I started with and multiply every piece of this equation by it. So left-hand side, I'm gonna have an x minus 1 squared times an x plus 3. And then I will continue that multiplication on each of these 3 fractions here. So I take this fraction, multiply it by that denominator of x minus 1 squared times an x plus 3. Replicate that here for the second fraction, multiply it by an x minus 1 squared times an x plus 3. And then last but not least, take this third fraction and multiply it by the same denominator, x minus 1 squared times an x plus 3. Again, we call this clear the fractions because in my very next step, as long as I did this appropriately, I should now have a new equation with no more fractions. So on the left-hand side, I have x minus 1 squared divides out with this x minus 1 squared. X plus 3 divides out with this x plus 3. That was all by design, so that I can now get just 10x minus 2x squared on the left side by itself. On the right side, what I have that divides out here is an x minus 1 with only one of those x minus 1s. So I had an x minus 1 squared, but only one of them divided out. So now what I have left, of course, is the a, and then one of those x minus 1s and one of those x plus 3s all being multiplied together. So I have a times x minus 1 times an x plus 3 for that first part. Then I continue on, and for my second fraction, well, this whole denominator of x minus 1 squared divides out with this entire factor here, x minus 1 squared, leaving me with just b times x plus 3. And the last fraction, just the x plus 3 here and here divides out, leaving me with c times x minus 1 squared. Okay, so the process is very similar to what it was in the last example we did. It's just more complicated in the sense that I have more pieces that I got to deal with. But I continue on. I want to go ahead and distribute everything that I have here on the right-hand side. So I have 10x minus 2x squared that gets copied down equals. Now over here, let's go ahead and just expand this by distributing out. Some people call that FOIL out. And then of course multiplied by the a. So I'll do that last though. So I'll keep my a here multiplied by, when I distribute, I get x squared plus 3x, but minus 1x, so plus 2x, negative 1 times a positive 3 times a negative 3 right there. So then I continue on. Let's go ahead and distribute our b. I have bx plus 3b. And over here, because I have to square the x minus 1, let's hold on distributing the c for now. And let's just go ahead and distribute x minus 1 times another x minus 1. So when I do this process, I have an x squared. And then minus an x times another negative x. So I have minus 2 x's total. And then a negative 1 times another negative 1 plus 1. Okay, we just keep trucking away here in this problem. I have an a that I should distribute, a c a little bit later that I should distribute. So I have 10x minus 2x squared equals ax squared plus 2ax. Notice how I wrote that, 2ax. We tend to do that because we know a is a constant itself. Let's push over to the right, to the end of this expression, the x. And then just continue distributing, so minus 3 times a plus, and then carry on, bx plus 3b plus, distribute the c. I have cx squared minus 2cx plus c. Okay, at least all my parentheses are gone. What I now need to do is strategize my work here. I want to group this stuff that has like terms together. So I want all the things that have an x squared, such as here and here, for those two terms, I want to put those next to each other. And then I have a term here that has an x, here that has an x, and a third one over here that has just an x, put those together. And then the 3a, the negative 3a really, the 3b, and the c need to be grouped together. So I'm just gonna move things around to accommodate. So I have, again, just rewriting the left-hand side, not really doing anything right now to the left-hand side. So 10x minus 2x squared equals, let's put the cx squared next to the ax squared. So ax squared plus cx squared. And I'm gonna go ahead and cross those out because I've taken care of them. And I will, now my next piece, I'll take care of my x's. So I have plus 2ax, took care of that, plus the bx, took care of that, and then minus 2cx, took care of that. All right, 3 more pieces now just to write down, minus 3a, that's gone, and then plus 3b, taking care of that, and then plus c. Again, all I've done is rearrange things so that in my next step, things are organized a little bit better. So I see here I've got these x squareds. Let's factor out the x squared in both of those terms. And similarly, I have a greatest common factor of an x in those 3 terms that I will factor out. And then these last 3 terms will just be grouped together. So I have 10x minus 2x squared equals, I'm gonna, in parentheses, just put an a plus the c, showing that I have factored out back here an x squared. And of course, if you want to check yourself, you just distribute that back in, and it's equivalent to ax squared plus cx. And my next terms plus, I will factor out the x, but I'll put it at the end. So here in parentheses, I have 2a plus a b minus 2c, and then here's my x that I factored out of both of those terms. And then over here, I just want to group the last three together. I'm always going to add here, and because this is being subtracted, I'm going to absorb that here on the inside of the parentheses. So I have negative 3a plus 3b plus c. Okay. All of that work to set us up for right now to be able to compare my x squared's coefficient, which in terms of the expression is a plus c, and I need to go on the left side of the equation and find the x squared and set it equal to its coefficient. So I have here an a plus c that will be compared to, in terms of equivalency, be compared to a negative 2, since a negative 2 is the coefficient in front of x squared. So right there, when I compare those, now I know in order for that equal sign to actually have meaning and be legit for the left side here equaling the right side, it's got to mean that a plus c is going to be equal to a negative 2. So we know that that's a fact. Okay. My next piece, this right here, 2a plus b minus 2c, is the coefficient in front of the x term. So this whole piece, when I compare it back over here on the left side, I see here's my x term. It has a coefficient of 10. So when I think about comparing those two, I have yet another equation set up. So now I have, let's see, 2a plus b minus 2c, this whole thing in parentheses, is equal to 10. Okay, so far so good. Now what do I do with this stuff that's over here on the right-hand side? Negative 3a plus 3b plus c. What does it equal over here on the left-hand side? Well, truth be told, these two are already taken care of, right? These terms that are sitting here. What's really sitting over here on the left-hand side that I can write in just to be helpful is, say, a plus 0. So now I can say, oh, this whole constant that's this equivalent to this expression of negative 3a plus 3b plus c, it must equal 0 since there was no just plain constant on the left-hand side. So that gives me my third equation. So I have negative 3a plus 3b, that's a 3, and then plus c will equal 0. All right, so I'm going to box this. All of that algebra so far has allowed me to at least construct the 3 equations and 3 unknowns that I need to now solve for. And again, like before, you have some choices on the technique that you can use to solve. You can use matrices if you're knowledgeable of matrices, or you can use algebra in terms of graphing, in terms of substitution, in terms of elimination. Whatever will work for you is what we can use. But now here, I think I'm going to leverage substitution again, and maybe a little bit of elimination as it kind of comes up. My eye automatically goes to this top equation of a plus c equals negative 2. It's appealing to me because it only has 2 unknowns. So let's take that equation and solve for one of the unknowns. Like maybe I'll solve for a by subtracting c over. Okay, so I now have at least a new equation that when I do that, I have a equals, how about negative 2 minus c? Okay, now I have these two equations down here. Both of these have all 3 unknowns, the a, the b, and the c. So what I can do to kind of, there's different routes I could take at this moment in time, but what I could do is collapse these equations by substituting in what I know a to be here in the second equation and in the third equation. And when I do that, I will at least have 2 equations with 2 of the unknowns. A will be gone. If I do this correctly, B and C will be remaining, and then I'll have to continue on with my algebra journey. So let's check that out. I will take A is equal to negative 2 minus C. I will plug into my second equation for all A's. It's only one place right here. So I have 2 instead of A. I will multiply it by a negative 2 minus C plus my B minus 2C is equal to 10. Okay, I will do the same process in my third equation. I will replace the a here, my third equation, with what I know it to equal. So I have now a -3 times, instead of a, it is going to be equivalent to -2 minus c plus 3b plus my c that I have here equals 0. Okay, so that's good news. I think I've got two equations here. I need to do some combining of like terms and simplify and continue on my journey. So let's see, if I distribute here, I'm going to draw a line for equals here. I'm going to continue right below this line and start with this equation. I have 2 times a -2, so this is a -4, and then minus 2c plus b minus 2c equals 10. Okay. My next equation, I do the same process. I will have 6 when I distribute here, -3 times -2, and then -3 times the -c, so that's a positive 3c plus 3b plus c equals 0. Okay, we're getting somewhere. Continue on simplifying as much as you possibly can. So now I have, I'm just going to move to the right here and continue. I have -4 minus 2c plus b minus another 2c. Let's do a couple of things here. Let's combine the -2c's and let's add the 4 to the other side. So if I do that, I have b minus 4c is equal to 14 when I add the 4 to the other side. I'll do the similar actions here to this next equation. I will subtract 6 to the right-hand side. I will take my 3c and my other c, add those, I get 4c. So I have 3b and then plus 4c is equal to subtract 6, just be careful with the negative sign, and now I have a -6 here on the right-hand side. So far, what I have done is I've leveraged the technique of substitution of these systems of equations to continue collapsing my equations down to a manageable number of unknowns, ultimately so that I have just one unknown left. Well, I'm almost there, but not quite. But if you look closely, let's actually use elimination as a method here to solve. Elimination says I can take these equations and literally add vertically down. And I can do that when I have, like for the C unknown, when I have the same coefficient but opposite signs. That's a plus right here. Well, I have a -4c, but later I have a plus 4c. So when I add vertically down, the 4c and the -4c subtract out, and so they're gone, they're eliminated. So let's see, I have a b plus a 3b, so that gives me 4b left over. These are eliminated entirely, and on the right-hand side I have 14 minus the 6 when I add down here, and that gives me 8. So now I have an equation 4b equals 8, and now hopefully you see that after all of that, we have at least one of the solutions. B is equal to 2. Okay, so this is awesome. Now that I know that B is equal to 2, we can start kind of backtracking in my work here to figure out how to get the A, how to get the C. So let's see, I know that B is 2, so if I go to this equation, either form here or here, it's not going to do much help for me because I don't have a B to substitute that B into, that 2. So I have to go to one of these, in fact, both of them, to actually plug in my B and see where I'm left off. So I think I'll take this second equation right here. I will substitute that I know B to be 2 right in its place. So I now have 2a plus the 2 instead of the b minus 2c equals 10. Okay. Let's do the same process with the last equation here. To eliminate essentially the b, plug in my 2, I have -3a. When I plug in my 2, that gives me a 6, that's positive, plus a c, and that will be 0. All right, we just continue working here, we would like to get some things either to eliminate or somehow manipulate so I can back substitute. So I'm going to just continue on. Let's simplify here. I see I have a 2 that I can maybe subtract over to the other side and generate a new set of equations. So I have 2a, subtract the 2 over, so I now have minus 2c is equal to 8. Below that equation, let's subtract the 6 over to the other side, so I have minus 3a plus a c is equal to minus 6. Now I'm almost ready though to eliminate perhaps the C unknown. We could do the A as well, but it's actually going to be a little bit less work to eliminate the C if I do this. I can imagine, again, having both of the C coefficients to match, like a 2, but one has to be a negative, the other has to be a positive. Here's a negative 2, here this is already positive. If there just was a magical 2 that I could put in front of that C, then I could eliminate, much like I did for solving for the B. So, well, we can do that. We can do whatever we want, but there's consequences. The consequences are I need to double that term here as well as that constant on the other side of the equation. In effect, multiply the entire equation by a 2 to finish solving. So if I do that, I'm going to leave my top equation as is. 2a minus 2c is equal to 8. I'm going to double the entire second equation, so minus 6a plus 2c is equal to negative 12. And then like I did before, let's just go ahead and vertically add down. This is that process of elimination. The c's eliminate entirely. What remains, 2a minus 6a, so that's negative 4a. Over here, that's going to be equal to a negative 4, 8 minus the 12, so a negative 4. And so then to simplify, I can now divide both sides of that equation. Right here, I end up with negative 4a is equal to negative 4. Divide by negative 4 on both sides, and I end up with a equaling exactly 1. Okay, that's good news. That's good news, because now what I can do is, now that I know what A is, I can now go actually back to this equation right here if you want, or you can go back to this version of the equation as well. But this one is more advantageous for us because I know what the A is 1, and I can use that to simplify and solve for the C. So I have here that 1 is equal to negative 2 minus C. Add the 2 to both sides. So I have now 3 is equal to negative C, but we don't want negative C, we want positive C. So you can think multiply through that equation by a negative 1 or divide by a negative 1, whatever the case is. No matter what, C is definitely going to be just negative 3. Okay. So now we have all of our unknowns, and by the way, just a reminder, the unknowns are in fact my numerators of my separated set of fractions back over here. A to be a positive 1 goes with this numerator. B is a 2 goes here for this numerator of that fraction. C being a negative 3 for the numerator there of that fraction. I'm not done. It seems like maybe I should be, but remember the whole point of this problem was to integrate this original fraction that we had that was very complex. So now we have a way to expand that one integrand into 3 separate fractions, and I will integrate each of those individually. Okay, now I'll return back to the original problem and rewrite this and finish off my integration. So I have here, instead of this fraction that we started with, we will have 3 separate integral problems, each with our new integrand, that's our fraction that we finished solving for. We found that A was 1, so putting that in my first numerator, we have 1 over x minus 1 dx. And then I will add to that here the integral of, we found that B was 2, so I have 2 divided by x minus 1 squared dx. It does matter that you get the correct a numerator with the correct denominator that you use to solve for it. So you can't mix and match. And my third one, I have plus the integral. We found that c was -3. So this is a -3 divided by x plus 3 dx. Okay, so let's see here. It turns out in this, for this integral, because like of the last problem, I have a linear factor that's here, this is just going to be the antiderivative of, and I would get natural log of this denominator. That would be my antiderivative. Same is true for this denominator over here. I would though need to go ahead and pull out that -3. This will take a little bit of work. So let me do what I can right away and then we'll go from there. So drop things down here. The first integral of 1 over x minus 1, that's simply going to be the natural log of the absolute value of x minus 1. The second piece here, let me just rewrite the integral as is, and we'll come back to it. This is going to be plus the integral of 2 divided by x minus 1 squared dx. And then over here, let's go ahead and factor out that -3. In which case, when I do, I'm allowed to pull out that constant multiple out front. But when I do, I then have 1 over x plus 3. So its antiderivative is natural log of x plus 3. Natural log of absolute value of x plus 3. And of course, I can't not have my plus c here at the end. But I'm not quite done because I have this piece here in the middle. And you might think, well, maybe that would work like the other two integration pieces did. Wouldn't it just be natural log of absolute value of x minus 1 quantity squared? No, it's not, because I don't have a power of 1 like I did here, that x minus 1 had just 1 as its power. Same is true for x plus 3. So how do I deal with a power of 2? Well, let's go way back. Substitution is going to be the technique that I will use for this one. So I'll just temporarily kind of come here and let's talk about the substitution. If we let u equal our x minus 1, our x minus 1 that's here, what I will then do is take its derivative. So I end up with a du equals, in effect, derivative of x is just 1. So dx is what remains right here. Du equals dx. Okay, so I'm just going to continue on and then I'll come back to my original problem here. So I have this integral of originally 2 divided by x minus 1 squared dx. And through u substitution, first of all, let's pull out the 2 and then replace the bottom part here. So I have my 2 on the outside as my constant multiple. I have now the integral of 1 over x minus 1 squared dx. But let's sub out all the x's and dx's for things that are used to make the integration here a little more manageable. So still have my 2 on the outside. This is now the integral of 1 divided by, well, instead of x minus 1 squared, this will be just u squared. Instead of dx, I'm going to replace dx with du. Okay. So now you might notice that in fact 1 over u squared could be rewritten as just u to the -2 power. So we have here 2 times the integral of u to the -2 du. I haven't actually taken its integral yet, but I can now, by switching around this fraction here and making that exponent negative, now you probably can see that all we're going to use is actually the reverse power rule, right? To find the antiderivative by adding 1 to this power and dividing by the new power. So we still have the 2 out front. Add 1 to this power. Be careful here because you have a -2, you add 1 to it, you're now at -1 for the power. So u to the -1, but now you divide by that new power, right? So divide this by the new power of -1. You can simplify this. 2 divided by a -1 simply as a -2. We're not going to leave this answer with u's, right? Because we have our x's originally. So let's sub back in what we know u to be, which is our x minus 1. So we have -2 times an x minus 1 to the negative 1 power. Okay, now at least I know what this integral is. So let's write it all out beautifully. So I'll just drop down here. This is equal to, let's go ahead and rewrite this first part, natural log of the absolute value of x minus 1, and then pick up here this integral of that's being added, so plus the integral of 2 over x minus 1 quantity squared dx in turn becomes this quantity. So I have minus 2 times an x minus 1 to the negative first power. And it's perfectly okay to leave this with a negative exponent. But if you really want, you could put it down in the denominator. But no need, you can leave it just like this. And then continue on, minus 3 natural log absolute value of x plus 3 plus c. And after all of that, I'm going to box this as my final answer. This is a pretty complex and involved integration by partial fractions, particularly when you have some quantity here being squared or some other exponent higher than 1. Okay, so I hope you enjoyed this particular video. Thank you for watching, and be sure to click on the EdVantage logo to subscribe to our channel. Thanks.